Are you online?
Yeah.
How'd you get online? What's the password?
Mars or bust.
Mars or bust. No capital.
No. No spaces, no.
Actually, yeah. Go and get another secret password.
It's different for
No, I'm just,
wait.
let's talk about the knowledge.
Oh, for that. Oh. What? Like, why is this different?
Just me and different.
All right. Yeah, we can reach to.
My name is Peter. I work for Boeing as a aerospace engineer, working in the entry aero heating subsystem. So we get to deal with re-entry and making sure that the vehicle is safe for re-entry. And I have 3 sheets of paper, but
There's more over there.
yeah, okay. So. Feel free to just jump in, ask questions as I'm going on, or if there's something in particular you want to know about. I'm just doing this off the top of my head. I love the shuttle. I wish it wouldn't go away. I think it's the greatest thing since sliced bread.
You think they can continue to extend it?
I would continue to extend it. I would fly in it myself.
I know they ask us for possible life extension just for the WCS and stuff, and we pretty much at the point in time though, we're not sure we can life extend any further.
Yeah, I mean, there's lots of, I mean, it might not be a practicality, but going back to both Mercury and Gemini were kind of this shape where you had the heat shield on the bottom, and Gemini is just a little bit bigger version of Mercury, but the reason they did this is they want this nice blunt end on here, and what this does is as you come in the atmosphere, what starts happening is you're coming in so fast that the air is literally being ripped apart. You got your oxygen and nitrogen is all being ripped apart, and it forms this shock wave, and the more blunt you make this shock goes farther away, and you want this farther away because this is the hot part, and you can get it to stay farther away. Well, the problem is this is basically a dumb system where it just comes in like a bullet. You have no control over it. They did experiments with Gemini where if you come in at a little bit of an angle, and a lot of what drives the controllability is on your center line. If you shift your CG off to the side, you can kind of start generating a little bit of a lift. And with that, if you look at the air, this is how high you are, as you're coming in over a certain distance, you're really high in the atmosphere. I know the ballistic one, it just comes shooting through the atmosphere really fast. And so both your speed and the air density increases rapidly and makes it really hot. Well, if you can get just a little bit of lift and fly higher where the air isn't as hard or as dense, it's a lot easier. And so with Apollo, this again was the same case. Now they had a little bit different capsule like this, but it's the same general idea. Is you want to make this as kind of a bigger circle as possible to try to keep that cool. So along came shuttle, and the whole reason with shuttle having wings was you come out here and you have wings, and the idea is you can generate lift with wings, and so you can, instead of trying to do just kind of tilt this a little bit and try to fly a little bit, you can fly a lot. And whereas temperatures on here might easily go to 3,000 to 4,000 degrees. There's on the shuttle, on just the very front of the nose and the wings are really the only spots that get anywhere close to 3,000 degrees. And then the technology as far as what they use can change too, because these both use what they call ablators, where you're basically burning off the material. All you're cooling that, the material carbonizing and flying away from the vehicle is what's getting rid of your heat, whereas shuttle, it actually radiates the heat away. It's almost like when you feel your oven on and you can feel that heat coming away from the oven. That's how it's getting rid of the heat. But the efficiency of using radiation goes up, I think it's to the 4th power of temperature. So if you get something twice as hot, it actually will get rid of like 32 more times heat than being twice.
I have a question about that. So, okay, so the capsules, they use the ablative material because they weren't going to be reusable. So the tiles on the shuttle were developed because, the shuttle was supposed to be reusable. So if you were to develop, I don't know anything about Orion and all that, but, did they put the tiles in the Orion capsule? Because Orion was supposed to be reusable.
And Orion is an ablative again. Okay. They actually, they were looking at using a newer material called, it's called Pica. What Apollo and the others used was called Avco. And the reason you have to go back to that is because you're taking the just straight shot down in the atmosphere again, and tiles can't take that much of the heat. The tiles will start, I believe they'll start slumping around 2,900 degrees. And so once you get beyond that, the tiles will start melting. And then, but the ablators can go a lot higher in temperature. So that's why on Orion, they kind of had to take a step back to this ablative technology. Now, you can make it, you might not be able to reuse a heat shield, but at least you can make it that you can just detach and swap out a heat shield and make a reusable capsule. I don't know how practical that is. And then the other tray on the tile, though, is you've got each of these little tiles, as you've probably seen on the shuttle, there's hundreds and thousands of these little tiles, and the reason is that they're really brittle, and so when they're attached to the metal skin, and the metal skin kind of moves and shifts, they got to be so small, otherwise if they were bigger, you start cracking those tiles in place. Whereas the ablatives on the older capsules, they're just a solid chunk usually. Now, SpaceX is actually, they're doing a capsule as well. And if you look at the bottom of it, they've got, it's an ablator called Pica X, which Ames developed Pica, which was this new generation ablator, and I guess SpaceX kind of tweaked it a little bit, and they made their own. And so if you look on the bottom of the SpaceX capsule, they've got these big tiles basically made out of this, and supposedly they can reuse their heat shield because their heat shield, they designed their spacecraft to come in from a lunar trajectory, and so coming in from Earth in ablative is really fast, but coming in from the moon, you see even higher temperatures. It's really unbelievable. But going back to the shuttle and being able to do this lift, you kind of have to make some trade-off. Well, there's some gains and then there's some cons. So the big thing in the shuttle is you can actually control where you're going. So like the Apollo missions, you're out, you've got this is my crude United States and over here, and so you got Australia out here, and so you got the whole wide Pacific Ocean to land in. Well, on Apollo, they'd say, okay, well, because we can't really control the trajectory too well because we can't fly, this thing's kind of just going down. So they had this whole area, like, okay, we might land somewhere in the ocean here. So, and Orion was getting everywhere. So like off the coast of California, we're going to be out here somewhere. I mean, that's a lot of areas. Where shuttle, we're going to land here. So, or back in Florida, something like that. And so that's the one big thing that wings give you. Now, going back to this, so these guys come in and they're in the atmosphere for like 300 seconds. The shuttle is on the order of like 30 minutes. And so you're not taking as much heat, but you're taking a lot more heat load. Or you're not taking the heat rate, but you're taking a lot more heat load. So there's pros and cons with that, definitely. Where I think shuttle went wrong back in the 70s, when they were thinking about it, so the guys who did Apollo said, hey, this system, it doesn't work that great. It's expensive. You got a lot of, you throw away these things every mission. Something shuttle went great. There was a NASA designer who actually was responsible for some of the earlier capsule design. He said, hey, you know what we need to do is we need to go, we still want a more blunt body, but we're going to make a shuttle that looks like this. And you can go and find the patent that he submitted online. But it looks like an airplane. It's very simplistic. And the idea is you can get a little bit of lift by taking this basically airplane-like vehicle and using it a little bit like a blunt capsule. So you got this nice blunt, on the bottom side it looks blunt. And then, so you're not generating, the nice thing about the space shuttle, you have these delta wings, and in the hypersonic regions, this gets a lot of lift for a really fast vehicle, whereas this doesn't get any sort of, or gets very small amount of lift. And so you fly it kind of in bluntly, just at a really steep angle. And then once you slow down, then you fly it just like an normal airplane landing. Now the reason this got thrown away was it didn't fly as well, really fast in the hypersonic region. So they were a little concerned about stability. They didn't want it to come in and start tumbling. NASA was having problems getting enough funds for shuttle, and they decided to start working with the Air Force a little bit. Now, Air Force didn't give them any more funds, but by saying, okay, shuttle is going to support both NASA and the Air Force, that made Congress more amenable to saying, okay, we'll give you the money for that. So the way that Air Force tagging on is they really needed the lift, and they needed to go to a delta wing on the orbiter, and that was because if you're launching a military mission from Vandenberg and you launch it in polar orbit and you actually go way south from Vandenberg, you go around the Earth and you come back around, well, the Earth is spinning, and in time that you do one orbit, your shuttle's over here now over the middle of the ocean. Well, if you have an emergency and you need to land, you can't land in the middle of the ocean. And so there's 1,200 miles was the distance between the launch site and the new orbit path. So the shuttle had to be able to actually fly 1,200 miles across range, across the ocean to get back to Vandenberg. Now, I think the main driver was emergency situations. I have read where they wanted to be able to launch a shuttle and be able to grab a Russian satellite and then land in one orbit before the Russians could do anything about it. I don't think, after seeing how shuttle operates, I don't see how anyone can see that possibility. But it does seem to be that once around orbit was the main driver to having to go to this delta wing shape. Now the delta wing shape, because of this, you're flying in. You can't fly in quite as steep. You got to fly in at a lower angle of attack, and so the shock wave comes off, and it hits this wing, and that creates this really high temperature here. So with this, you're coming in a lot higher, and the shock wave kind of just goes around the vehicle, and you don't have it.
Shock getting like the friction when we escape the atmosphere?
I'm sorry?
What kind of shock are you talking about?
So in just in fluid dynamics, where you have like a shock off when a plane goes supersonic, you get that shock wave that's out in the vehicle, and what it is a compression shock wave as that fluid accelerates. Well, it depends on which. If you're in the free stream, it's decelerating or vice versa. But anyway, the air is really it has a very low density, and because this vehicle is coming in so fast, it's got a very high density, and so it forms a very hot compression there. And for like supersonic vehicles, shocks aren't really that bad, but when you're coming in really fast, these shocks they'll just melt anything that you stick in them, unless it's a really, really high temperature ablator or something like that. They can get very powerful.
And I'm not in aerospace at all, but this is interesting. Are there multiple shock waves?
Yeah.
And where is their spacing? Like how far apart are they? So
I'm
sorry to off track your time.
Oh, no. I started out by saying, please, and anytime feel free to hop in. So,
Let me move the mic. I think I had a complaint about if you would move forward with it.
okay. Yeah, I can do that.
I'm sorry, just want to make sure.
You might need to actually.
Yeah, if you
Someone online, Jeff, says there are two shock waves, one from the nose, one from the wings.
Right. Yeah, you'd have so off of something like the space shuttle. Well, actually, so from fluid dynamics, you actually get a couple different shocks. There's a compression shock wave where the less dense air gets compressed and decelerated, and then you have what's called an expansion shock, where I'll show that here. So on a shape like the shuttle, what we're primarily concerned with is the big bow shock. This is where you're taking a less dense air and it's going from what we call a Mach number, which is the relative. It's the ratio of the speed of sound to the air. It makes a lot more. It's a non-dimensional number that kind of you can apply it apples to apples to different vehicles.
So the speed of sound is different, supposedly, theoretically, right? The speed of sound?
Yeah, speed of sound. So this is, so Mach 25 would be about 25 the speed of sound, and that's where we start seeing some of the atmosphere in the shuttle. So you're taking this this air that's going Mach 25 and you're slowing it down to zero here, and it creates this big, powerful shock wave. And so you've got the nose creating a large shock, and then you also have the wings sticking out on the side, and they make their own shock. And where these two intersect, they compound the issue, and they hit the wing here, and that's why you have those specialized RCC panels on the wing of the vehicle. And so, and then the second type of shock, you'll get kind of the air will kind of accelerate as it goes around turns again, but then it'll accelerate here and then form another smaller shock. Anywhere you have protrusion or something like that is going to create shock waves. But the primary is the bow shock and wing, and that's what happened to Columbia, is when you had a hole here. Yeah. I mean, this hot gas just gets in there, and that was just at the weakest point in the vehicle. So what would have been nice if NASA had gone with this straight winged orbiter. By flying it higher, you don't have this intersection. They wouldn't have had to use specialized RCC on the wingtips. You would have only seen maybe just a little bit on the nose cap there. And then the other way that the Air Force influenced was they needed a very long payload bay. NASA actually wanted to build station modules. They just needed, they wanted the diameter, And then the Air Force really didn't want the diameter, but they wanted the length for their spy satellites. So you ended up with this much larger payload bay than NASA would have needed. The whole vehicle got bigger and then heavier, and then it flies. The heavier something is, it comes down through the atmosphere faster. So if they had gone with a lighter vehicle, it wouldn't have seen the loads that they have. So as far as, if I was to right now build a space vehicle, I would probably want to go back towards something like NASA originally envisioned in the late 60s, early 70s with the straight wing orbiter like that. And then the other big thing on entry is, are people familiar with laminar versus turbulence? So actually, the beautiful thing about working in entry is the air is the Reynolds number, or I should specify something. What a Reynolds number is. Reynolds number gives a quality of turbulence or laminar, and so for very low dense fluids, the Reynolds numbers are small, and it's a laminar flow. Whereas for a high speed, or once you start getting a thicker atmosphere, the Reynolds numbers get higher, and so you get turbulence. Like we see turbulence often on jetliners and things like that. But for the very early parts of entry, shuttle is actually really simplified fluids. It's laminar fluid. But if you look at the heating at one point on the vehicle, so you'll come in and it'll be really low because the air isn't really dense. But as it starts getting into denser atmosphere, the heat gets up really high, and then and we actually have thermocouples or temperature sensors on the skin that tell us this. But then you'll be coming along, and then it'll just spike up like this. And what's happening here is the flow has transitioned from laminar to turbulent, and it really drives the heat rate. It's more efficient at transferring the heat from near the shock towards the vehicle as it's more mixed.
The temperature versus position?
Yeah, this is temperature versus time. And I should probably make this 15. And then it'll start coming down again. And so that's another driver in reentry is if you were to start with designing a new vehicle right now, I couldn't tell you when this happens. There's really the only way to do it is there's wind tunnel testing, where you go into the wind tunnel and you would run it at different what we call Reynolds numbers to try to figure out, okay, and not only is it vary per ton, but it also varies wear on the vehicle. So the aft part will actually see the most, so turbulence will start getting created. Well, the physics that set up turbulence start getting created up here, but you'll actually start seeing turbulence down here on the bottom of the vehicle, and it'll slowly, as time goes on, it'll slowly start covering more and more of the vehicle. And that can be an issue. One of the big things with the gap filler on the SS-114, because that gap filler sticking out will cause this turbulence. And so the gap filler was right up here on the nose, and what they were concerned with was this was going to, because normally the vehicle will, if you have no protrusions, all smooth, everything, the vehicle would transition somewhere around between Mach 6 and Mach 8. So and actually that's past most of the heating. You're almost down here at the as far as the heating level. So if you see transition here, it's only going to go up a little bit. Whereas if you transition up here, you see a huge increase to your heating. And so what would have happened is, if it had stayed in, was this whole part of the vehicle below this would have been turbulent, really high up here, and it would have just really soaked into the vehicle.
I have a question about the shock and the heat. So after you reach the speed of sound, you get a sonic boom. But past that point, the friction of the air drag is significantly lower. But why is that?
The air drag is significant? Yeah. Oh, you're talking. So I guess it. So So if this is Mach this is drag. So at Mach 1, you're talking about the drag suddenly increases and then it decreases like that. That's from the.
I'm assuming that's why also the temperature decreases, after you go through shock, right?
Say that question again. I'm sorry.
So I'm assuming that's just that correlates with the fact that the temperature decreases within time.
Actually, well, as far as the heating on for reentry level, you do get this would give you a little bit more friction, but down at these lower Mach numbers, and you're not really seeing that much heating to the vehicle. You're right, but what really becomes the driver as you go up the even higher Mach numbers, what's really driving the temperature isn't so much friction, but the fact that you're taking this air and you're compressing it into a lot more dense, and that's what creates the heat. So it's almost just the fact that I mean, you're just surrounding this vehicle with huge amounts of heat, whereas it's not so much as a frictional process, but this compression process. Whereas down here, the lower Mach numbers is more of a frictional process.
So why is there significantly less density of air or the air drag after if you go higher than
so if you're in a normal airplane and you go above Mach 1, what it is it's maybe someone online might be able to speak it a little bit better, but flows don't like being around exactly Mach 1. It's just the fact that everywhere is sonic, and so it almost becomes a whole shock wave, no, not really the case, but it's just that transonic induces a lot of, I don't know, I guess I don't really have an answer to you as to that, but I know, but I do a lot of fluid dynamics computationally, and we usually, if we do a simulation, if we want to know around transonic, we usually do a simulation at Mach 0.95 and Mach 1.05 because the numerics become unstable at exactly 1. So we kind of interpolate between the two. Okay. But I think that covers most of what I had off the top of my head. This is most of what I deal with on a day-to-day basis.
How do you deal with the thermal expansion?
Thermal expansion?
Right.
I'm not a structures guy, so I don't care about it. But it really is an issue. I mean, it's something to take into account. It's amazing when you consider the way they've got these tiles attached. Is so you have your tile. And they actually have this, the word is eluding me right now what this is, but it's basically like a rubberized pad that they attach the tile on, and it's made of RTV, and then you have the aluminum structure. And so, I mean, aluminum it melts pretty easy. So you would think that they wouldn't really want to use this in an re-entry vehicle. But these tiles are so great at insulating it. So you might see something like 1,200 degrees out here, but here it's only like 180. So we really want to make sure that this material doesn't get above 250, and this filler material doesn't get above like 5. I think 500 is really, it can go up there, but you're going to have to scrape it off and replace it the next mission. So I mean, this is a huge temperature gradient. So yeah, you have thermal expansion issues. So that's why the tiles are only, I think the biggest is 6 inches by 6 inches. Otherwise, they would start cracking from thermal expansion. And then this filler bar, kind of acts as to protect the tiles from the expansion of the metal. So this metal can expand, but because you got this rubber material, it can kind of shift side to side there and allow that to happen. But you have to be careful, again, with the gap fillers. If you start having an early transition, this part of the vehicle is really hot, and then this part of the vehicle is cooler, and you can start running into structural issues on that. So that's something that we pay attention to a lot, is not only do you have to make sure that the vehicle doesn't transition early, but when it does transition, you really want to see it go over the whole vehicle and not something like this.
I forget, but you know how like the shuttle has like 2 color tiles, like the black? They're for different temperatures, right?
Yeah, this point. So the equation for, so it's most of the heat. So you get this heat load applied to the tile, and something only like 5% of that total heat load goes into the actual tile. The rest of it is you've got this black coating on there, and it's radiated away. And the equation is so it's a function of the Boltzmann constant, the emissivity, and the temperature of that tile to the 4th power. So and that's the heat rate that goes out. So the higher this temperature, this heat rate.
We're getting requests from people online so they can see the. Thank you so much.
Oh, no problem. And that's what makes it, by radiating the process out, and what the black or white tiles control. Emissivity is a little bit part of it, but they're actually pretty similar. It's the catalyst. One of the things you also have to deal with is this shock. The shock wave that we've generated has stripped the oxygen goes to it's 2 oxygen atoms, but the nitrogen is also partially stripped to its 2 nitrogen atoms. And what they like to do on this surface, on bare surfaces, is you'll have 2 oxygen ions come together and hit the surface at the same time, and then they'll come back away as this O2 again. But the energy from these actually gets released as heat into the vehicle, and so and that's called catalytic heating. And so that's something that you really have to be aware of, because it can almost double your heating in certain situations if you don't take this into account. So that special black coating on the bottom of the tiles is a non-catalytic surface, so they can't hit it and combine, whereas if you have something like a metal or something like that where it loves to run catalytic reactions, it'll go like that too. So that's why you see the black on some side, and then you have the white tiles mostly on the upper surface where catalysis isn't an issue, and then they actually have blankets in really low temperature areas where they don't have to then worry about the material being really brittle or anything like that.
Can I ask you, I wanted to ask another question. One of your previous pieces of paper showed after the boundary layer, so at in your temperature over time, there's
right, yeah, when it goes turbulence. So
that's when the Reynolds number starts to go from, I guess, laminar to more turbulent. But how does it start cooling again?
It starts cooling because your Mach number is decreasing.
Okay, so that's just a function of where you are.
Yeah, okay. So really the primary heating is a function of the Mach number, and then you start getting secondary effects like laminar turbulence, things like that. So.
I have a question.
Yeah.
So oxygen is stable, it's a dipole, so it's stable as, O2.
Right.
But then they separate and they combine at the surface?
Yeah, so this shock will get up to a couple thousand degrees, and so suddenly the stability of the oxygen. It can't stay in that state. To get rid of that energy, it separates at that point. And so so if you just take air and you increase it in temperature, the first thing, so the air will just start heating up, and then well, I guess this is as you're adding really energy into it. So the air will heat up normally. So O2 will stay O2, N2 will stay N2. Well, the first thing that'll start happening is you'll reach a certain temperature, and those O2 atoms want to break apart, and so you'll reach a point there where so you'll have a mixture of N2 plus you'll have some O2 and then some O atoms in this region, and then usually you dissociate most of the oxygen as you reach up before you start dissociating nitrogen at that point. And then, because the nitrogen really takes a lot of energy to start breaking that apart. And then even if with some of the higher processes, or some of the higher speeds with Apollo, then you actually have to start worrying, you've gotten the air so hot that you're starting to strip electrons off of it, and you start making some other compounds. You start having to worrying about NO, I forget, it's not
Nitrous oxide?
What?
Nitric.
No. What?
Nitric oxide? Yeah, okay. Yeah, so you can, there's really, the higher in temperature you go, the more you have to start worrying about things. And then even, for Apollo coming back from the moon, what they have to worry about is, so they're trying to do, they're taking most of the heat by this ablative, and then you got this shock wave. But then as it starts getting hotter, they actually start relying a little bit more on the radiation. So the heat's going into the vehicle, but then you got some of the heat going out. But then once you start getting the higher temperatures, this actually becomes opaque to the radiation. And the radiation, this will actually start radiating back to the vehicle. And so then you start getting crazy weird stuff with statistical mechanics and all that, trying to figure out the radiation levels. But the nice thing about shuttle is we actually don't even worry about the plasma, really. It's just mostly we do a 5 species most of our simulations were 5 species, so it's O2, N2, O, and then a little bit of NO. And so those are the chemical reactions that you have to take into account most of the time.
I never knew that there was chemistry involved in it.
Yeah, it's a really neat process. Yeah, and it comes into play a lot more because, I mean, the nice thing about tile is that if it's a concern, you just throw this catalytic coating on it and you're done. With the RCC, it becomes a lot more of a black art with because it is a slightly catalytic material. So you've got a silicon coating. It's carbon-carbon is what they do. So it's really basically what they do is they take some they call it phenolic material. It's like a plastic almost, and they just bake it into an oven, and they just keep baking it, so if it gets any, they'll bake it and some of the material will get removed. They'll cram some more material in the holes that it makes it, and so it's basically just this solid chunk of carbon when you're done with it, but it's really brittle, and that's why in Columbia it had an issue with the foam hitting it. But then it will oxidize very easily because it's just carbon, and it'll love oxygen. I mean, it'll especially love this loose oxygen hitting it. So they put a special silicon coating over it. Well, and so that's what they're doing when they're doing those scans when the station is on orbit. Is they're going over that coating and making sure there's no little holes in it, because even if they don't have an issue with something hit it, and it doesn't even make a hole, but it exposes this. It's something like if you have something like a dime-sized spot where you've lost a coating, it could burn through on re-entry or something like that. But whereas like a tile, if you were to lose this little spot of coating, I mean, they've had tiles where they've lost maybe like 50% of the coating on it, and it's just fine.
You mentioned, like, I know that the shuttle tiles, for the most part, have to be completely refurbished after every mission, or a lot refurbished. A lot of work goes into them.
Right, there is a lot.
So, I guess how is there an advantage for using a shuttle where you have to mostly redo the heat shield versus a capsule where it's not reusable at all?
Yeah, there's a lot of pros because I mean, obviously going to the shuttle program, people thought that tiles were going to be great. Now you actually don't have to refurbish them all. It's just only the damaged ones you need to go and replace. So I believe that since the Columbia accident, they've done a lot of work on refining the processes that they haven't had to go and do as much rework between missions. So that tile rework has actually come down. So it's more of like a process control thing than anything else. But yeah, they were actually considering doing ablatives on shuttle at some point, just as kind of like an interim step. So I mean, it's possible to go that route with an ablative. The big thing is it also takes away some of your landing capabilities because the ablatives, how they burn, is a big question mark in the aerodynamics. So you've got this thing and it's off-gassing and it's changing your aerodynamics, and so you're not quite as sure where it's going to land, so your landing footprint gets a little bit bigger. And you can compensate that by being able to fly, but with something like Apollo, the aero difference is you can't really adjust for it, so that's why you've got this wide footprint with Apollo.
And what is the relative, how much weight trade-off is there in addition to that? How heavy
The ablators are, I believe, heavier. They're a lot more dense material. But you don't need as much of it. So it's a big trade-off is there. I believe they were looking at doing some tile type stuff, but it comes down to the high temperatures. Is the tiles just can't support it.
So what do you know about DSOs? There's a DSO, I forget the name of it, but in your field, where I believe in the next couple shuttle flights, they've got like little ramps on some of the...
Oh, the DTO? So yeah, that's a one of the things that I've got to be involved with a little bit was we don't know the characteristics of the boundary layer transition a whole lot. They've actually had some accidental trips on a vehicle that they didn't know about before Columbia, where it actually did transition at these really high Mach numbers. And instead of being this nice, so instead of being like this nice like transition like this, like, oh hey, if you stick something up this high, it gives this much. It kind of like goes like this, and it's like, okay, well, did we transition here? Did we transition here? And it becomes like, in what kind of function is that? So the nice thing about, and the thing is they can go and look at the gap fillers after the mission, but I mean, they're really floppy things. How high was it at this speed, or was it bent over? Or there's no traceability back into it. So people have been able to play with this a little bit, but the DTO is they've taken a tile and they've put a nice smooth bump on it, and it's more tile where they've just taken a larger piece of tile and just carved out this piece, and they put little temperature sensors up here. But the big thing is they know the exact height of this during the whole mission. Now so STS-119 they did a 1/4 inch height, and then I believe the next, this is all just on one vehicle right now, on Discovery, which is actually flying this next mission at the end of the month. So they're going to fly.
Decides to launch.
Yeah, if they ever launch it. So the next mission after that, they did a 0.3-inch one. And then this upcoming mission, they're going to do a 1/2-inch one. And so they're really getting up there, and the higher it is, the sooner it will transition. And the thing is they did this, and it's not getting as hot as they expected. They thought maybe that this would maybe be like kind of slumped off a little bit, like pressed down. Especially when they went to 0.35, they're like, yeah, we're gonna melt that sucker for sure. And now it's like, well, we hope we melt it off of this one. So it's throwing a big question mark out there in terms of being able to simulate this stuff accurately. But yeah, what also would have been nice is we do most of our mission support is when you have a cavity where something has come along and hit the tile, and you get this huge gouge in it. It's like, okay, well, how much material can we take out before this filler material gets to 550? And then if it's that bad, then it's like, okay, well, if it gets to 550, when does it go? And that starts becoming more and more a question mark. But you can actually take off a lot of material on the tile before you start really having a lot of issues. Because I mean, one nice thing is if it gets really hot here, you've got this other area to go and conduct the heat off to. So that becomes it would have been nice if they had been able to do a corresponding experiment by having a nice tile like this. Now, we actually, if we see something like this, the first thing we do is go and simulate something like this, because trying to model this is really complex. And I mean, it's hard. We in a mission, if we've got to do 3 or 4 of these in a 24-hour time frame, because so our group will come in and we'll go, okay, well, it's going to get like this hot here, and then it's going to get a little hot down here, and the nice thing about cavities is you've got this really fast flow going by here, and it's going so fast it doesn't really have a lot of time to turn. So this top corner will get really hot, but then the flow will kind of recirculate in here, and it actually adds kind of like a cooling effect. So you might get, the heating might be like maybe 1/3 of what it is here as it is up here. So it's still a wide field as far as being able to model this. I'm presenting a paper in July on actually trying to model this whole complex geometry, because the nice thing about the OBSS is it's got this laser scanner on it, give you a point cloud, and so we can just take that point cloud and just plug it in our model and go with it, versus just modeling it. I mean, really the biggest thing is with this is when we get a little picture from the shuttle does what they call an R-bar maneuver, where it comes up to station and it just kind of does a pirouette, and then they take pictures of it. But I mean, you're several hundred feet away, and they've got these really nice cameras, but I mean, you kind of like get these pictures like, here's a bunch of tiles, and it's like, okay, well, we see the coating's missing there, but is it just that this black stuff's gone, or how deep is that? We have no idea. So they've been able to actually advance this a little bit by, if they have staggered pictures from 2 different views, they can actually do photogrammetry. But if you get the sunlight on the white, you can't tell the details in there. So and that's a big thing issue is just the photographic issues with doing this. Is you're taking pictures of white stuff on black or black stuff on white, and just it'll saturate, or so it throws in a big question. And
So I mean, the photo guys are great, and they'll come back to us and go, okay, well, we see something sticking up, and we think that it's a 1/4 inch high, but it's plus or minus 2/10 of an inch. So it could be 0.4 high, or it might not even be there almost. So, and it'll come back, it's like, okay, we'll plug in the 3 different heights. And it's like, well, obviously this one's fine. This one, I don't know, if it's that high, we're not sure. And then this one, obviously, yeah, whatever. So it throws a wrench in the work, and especially with all this uncertainty in each one, that's a lot of what led to the 114 gap fillers being filled. Is it's like, okay, the photo guys got, they've got their uncertainty in their height, and then we've got our uncertainty in our models. So in our models, might say, okay, we might transition here and give you this curve, or we might transition here, but then you throw in the extra height, and we're going to transition over here. So you got this, if you start stacking up all the uncertainties, and then you get the thermal guys if they're uncertain, because we just tell the heat rate, we go and hand it off to the thermal guys to look at this, and then the stress guys get the thermal results, and they tell you if the actual vehicle is going to be okay. So.
Exactly. Yeah, they don't want. Cool.
Any other questions? All right. Well, thank you for listening.
If you would state your name again.
Oh, Peter McLeod, and I work for Boeing.
You got a compliment, by the way.
Okay.
And you went to UC Davis?
Mm-hmm.
Yeah. Yeah, I went to Davis for residency, so
okay.
moved from there.